So we were looking at the microcanonical ensemble, which, as you recall, we said is for an isolated system, and the density of rho e was 1 over omega e comma x. This is the total number of microstates, the omega of microstates given E comma x, the generalized coordinates and the energy. Now the examples that we did in the last two lectures was for discrete systems. We looked at two-level systems which were of main interest, and correspondingly, in one case we had 0 and epsilon, and we had in the second case we had the magnetic spins which could take +1 and -1 values. Now we want to look at the case where my microstate can take continuous values, the ideal gas. Here, of course, you are familiar with the picture that we have n particles which are confined in a box of length, or let's say a box of volume V. So an ideal gas is the one where you do not have any interactions. Actually, this is not a right statement, but essentially you have weak interaction so that you can neglect them, right? So one should not say that an ideal gas is without any interaction, interparticle interaction, but your state point is such, your thermodynamic state point is such that the interaction is very, very weak. For example, your density can be very less, the temperature can be very high, so on and so forth. So the Hamiltonian of this system is sum over I pi square over twice m, right? And this is equal to E, which means pi square is equal to twice me. So if you are looking at this in the phase space, then it's a hypersphere in 3n dimensional phase space. Note that the Hamiltonian does not have any interaction, and therefore the coordinate is not there. So the sole representation of the phase space is your momentum, right? So now I want to determine the total number of microstates, and the total number of microstates is the volume which is contained within the phase space, so that is going to be dq1, dq2, all the way up to dqn, integral dp1, dp2, all the way up to dpn. But now this also has to be satisfied, right? So that the volume of this happens over the region of R, where, well, let's say over the volume where sum over pi square is equal to twice me. Correct? Q1 is allowed to take a volume V. So therefore, this part is going to be V, and this part we will denote as omega p, where omega p is the volume of the hypersphere in the momentum space. Right? So we just have to figure out the volume of this. So omega p is going to be integral dp1 dp2 all the way up to dpn, and you have a theta function r square minus p1 square p2 square pn square, where r square is equal to twice me, right? So this is the volume that we have to calculate. Let's say that omega p is going to be a3n r to the power 3n, right? So this is what we start off with. We now have to figure out what is a 3n. For this, let's consider the integral minus infinity to plus infinity dp1x dp1y dp3n comma z, sorry, this is dpn comma z, e to the power minus p1x square p1y square, so on and so forth, all the way up to pn z square, right? Now this integral, I know each of this is a Gaussian integral, and therefore this integral is pi to the power 3n by 2, right? But if you look at this integral carefully, then I can recast this integral in this form, since it has a spherical symmetry. So therefore I can write down the same integral as integration of dp1 dp2 dpn e to the power minus p1 square p2 square pn square, which I write as dr d omega p dr r to the power 3n minus 1, right? 0 to infinity. So this is typically the volume of e to the power minus r square, because I have sum over pi square is equal to r square. Since this part is spherically symmetric, I take this measure and represent it in spherical polar coordinate system. This is the angular part that you have, and using the form of this, I have 0 to infinity. I'm sorry, this is just not going to be r to the power 3n minus 1. This is wrong. So it has to be e to the power minus r square. That's all, right? Now if I use this d omega dp, then this becomes a3n r to the power 3n minus r e to the power minus r square, correct? So that this integral is a3n 0 to infinity dr r to the power 3n minus 1 e to the power minus r square, and this is going to be a gamma function. It's going to be 3 by 2n a3n gamma 3n by 2. This implies that 3n by 2 a3n gamma 3n by 2 is pi to the power 3n by 2. So that I can immediately write a of 3n as pi to the power 3n by 2 gamma 3n by 2 2 by 3n, right? Okay, so therefore the total number of microstates EVN becomes v to the power n. There is going to be, there has to be an r over here, right? Yeah. So r to the power 3n, where r is equivalent to twice me, pi to the power 3n by 2 gamma 3n by 2 2m by e over 3n by 2 divided by gamma 3n by 2 plus 1. So this is going to be the answer for omega 3n. So if you have not yet followed this, then we will very briefly go. We consider the system of an ideal gas where there are n particles which are confined in a box of volume V. Therefore, the Hamiltonian of the system is given by this, which means that in the phase space, the Hamiltonian does not depend on coordinates. So in the phase space, it's just a sphere, in a hypersphere in the momentum space, right? So all I have to do is, in order to calculate the total number of microstates as we have illustrated, we just calculate the volume that is available between the energy 0 to E. And that volume is essentially given by this, where the integration of the momentum should happen over a region where pi square equal to this. And therefore, once you write down this as each of these coordinates q1 can essentially take values v. I mean, they can be over the volume v, and therefore this part of the integral gives you v to the power n, and this is the part which gives you omega p, which is nothing but the volume of the hypersphere in 3n dimensions. That's it. Now one has to figure out how to calculate this volume. Let's say this volume is a3n r to the power n, and this is not very different, because I know for a 3-dimensional sphere it's 4 by 3 pi r cube. So this is the part which is a3, n equal to 1, right? If n equal to 1, then if you go back over here, then the determination of a3n happens by just looking at this integral. I can separate this integral as each of these integral as product over I integration dpi e to the power minus pi squared minus plus infinity, and each of this integral is pi to the power half, so that if you take a product of all these integrals, there are 3n such integrals, and therefore you'll have this to be pi to the power 3n by 2. I can take now closely, since I can write p1, or let's say pi x square plus pi y square plus pi z square as pi square. I recast this integral in this form because I want to use the spherical symmetry of the form of the integral. Since the integral is spherically symmetric, the measure which was in the Cartesian coordinates, as you have seen earlier, now is converted to spherical polar coordinates. And then the rest of it follows immediately, so that you have omega evn, ln of omega evn is n ln v plus 3n by 2 ln 2m pi e minus ln gamma 3n by 2 plus 1. Therefore, the entropy takes the form is kb ln omega evn c3n, right? Which in our case is going to be omega evn h to the power 3n by n factorial, because these particles are indistinguishable particles. So you cannot distinguish between 1 and 2. This gives us, let's calculate this, n ln v minus plus 3 by 2 n ln e plus 3 by 2 n ln twice m pi minus ln gamma 3n by 2 plus 1 minus 3n ln h minus n So we will write ln n factorial. We will next use Starling's approximation to write down the gamma function and the factorial function in the following way. So the approximation that we are going to use, that since n is large enough, this is going to be gamma 3n by 2 plus 1 is going to be 3n by 2 factorial. Therefore you have ln 3n by 2 factorial, which is 3n by 2 ln plus 3n by 2 minus 3n ln h minus n ln n plus n. So let's take n common. I have n kb outside, ln v plus 3 by 2 ln e plus 3 by 2 ln twice m pi minus 3 by 2 ln n minus 3 by 2 ln 3 by 2 plus 3 by 2. There is, since I've taken n outside, there is going to be plus 3 by 2 here, and there is going to be plus 1 here. That gives me 5 by 2 minus 3 ln h minus ln n. So that this is going to give me n kb. Let's bring together the terms which I am interested in. 3 by 2 minus n gives me minus 5 by 2 ln n plus, so we will just write down minus ln of kappa, where kappa is a constant which you evaluate by plugging in these terms together, plus 5 by 2. And you see that this expression takes the form ln v e to the power 3 by 2 n to the power 5 by 2 kappa plus 5 by 2. Exactly the form of the entropy which we derived for an ideal gas when we are looking at thermodynamics using the Gibbs-Duhem relation. Except the difference now is I exactly know the form of kappa. If I just want to take care of, if I just want to look at these, put in all these three expressions, combine them into a simple one, I exactly know the form of kappa. So once again, statistical mechanics, first of all, the approach that we have taken gives you the correct expression for the entropy for an ideal gas, number one. The second point is this quantity kappa is exactly known. So del S, del E, V and N held constant is just 3 by 2 NKB by E, and this is equal to T, so that for an ideal gas you have 3 by 2 NKBT in accordance with what we did earlier. Second, del S, del V E and N held constant is P by T, which is going to be NKB over V, which implies PV is equal to NKBT. This is also the equation of state which you are very familiar with. So our expression for entropy, the way we calculate it by calculating the microstates contained within the volume, gives us the correct equation of states, the correct entropy that we have seen in thermodynamics. Both E equal to 3 by 2 NKBT as well as PV is equal to NKVT are experimentally verifiable, and they have been verified also. Therefore, our microscopic theory stands on a firm footing. We now want to look at a different classical system which is a very, very simple model for a solid. So we want to look at an ideal classical solid. And the model is very simple, that I have a one-dimensional lattice where at each of these lattice points I have atoms which are sitting, and I have a harmonic potential at each of these lattice points, right? So that the Hamiltonian of the system is half m omega square xi square plus sum over I pi square over twice m, right? Now I want to apply, this system is isolated, and therefore I want to apply our microcanonical ensemble to this system and try to figure out the entropy of the system, correct? Okay. First note that if I substitute Qi is equal to m omega xi, this would imply that xi is Qi over m omega, which means that the Hamiltonian now takes the form sum over I Qi square over twice m plus sum over I pi square over twice m, and this is going to be a constant energy. So in the phase space, then this equation Qi square pi square is equal to twice me defines a 6n dimensional sphere. Of course, the picture that I have drawn over here is purely one dimensional, since if you have a one dimensional system, then essentially you have a two-dimensional hyperspace, n coordinates and n momenta. One dimensional, you have 2n degrees of freedom, therefore this is the dimension of phase space. Two-dimensional, this goes to 4n, and three-dimensional, this goes to 6n. So if you are thinking about this in 6-dimensional, one has to be careful in putting a vector sign in all of these, right? Alternatively, you can say that I runs from 1 to 3n. Alternatively, if you want to avoid such confusions, you can simply say Qi square plus pi square is equal to twice me, where I is equal to 1 to 3n. That's all. Good. Now, you see, this is a sphere in the 6n dimensional phase space. And I know the volume in a 6n dimensional of a 3n dimensional hypersphere. We just calculated this for an ideal gas. So our total number of microstates, E and N, is going to be the volume of this 6n dimensional hypersphere. So that is 6n by 2 twice me, 6n by 2 divided by gamma 6n by 2 plus 1, right? This is just, we had earlier that omega p, the volume, was a3n r to the power 3n. Here, of course, the dimension is 6n, so this becomes a6n r to the power 6n, and this is the expression that you should have. So one can simplify this in writing twice m pi e 3n divided by gamma 3n plus 1, right? So this is clearly the hypersphere when you consider in this coordinates qi and pi, but we started off this real space coordinate xi and the momenta pi. So for us, if we we'll just change this. Maybe we change this over here. We write this as gamma E comma N. So if I want to calculate omega E comma N, the proper calculation is going to be dxi dpi with a product. Okay, let's just write this carefully. So d cube xi, d cube pi, and a product over this integrals, right? And this is 1 over h to the power 3n. Well, the 1 over h to the power 3n will introduce later on, but right now we just want to write down xi is q over, so this becomes 1 over omega raised to the power 3n integration product over I d cube qy product over I d cube pi. So this only tells you that these are in 3 dimension. Right? The measure itself tells you. But this we just calculated. This we calculated over here as this. So this becomes our actual total number of microstates is twice m pi e over 3n divided by gamma 3n plus 1. I can simplify this twice m pi e over m omega raised to the power 3n 1 over gamma 3n plus 1. Well, one can check this out very nicely, and then essentially you have S, the entropy of this system is Kb ln omega En, the total number of microstates, divided by the constant to make it dimensionless, which I have as 1 over h to the power 3n. The 1 over h to the power 3n, I can plug it in over here in writing e 2 pi e by h omega raised to the power 3n 1 over gamma 3n plus 1. Right? Now it's in a very elegant and simple form. So I have Kb ln e over h bar omega raised to the power 3n 1 over gamma 3n plus 1. For large enough n, I can approximate the gamma function again by a factorial, which becomes Kb ln e over h bar omega raised to the power 3n 1 over 3n factorial. Right? So S over E comma N, let's now expand this, is 3n Kb ln E over h bar omega, this is dimensionless, minus 3n ln 3n plus 3n. So this is the entropy of your ideal solid. Del S del T, del S del E, n held constant. There is no volume which appears over here because your Hamiltonian itself now depends on the coordinates. It's just 3n Kb over E and is equal to 1 by T, which implies that the energy is 3n Kb T. The specific heat, which is del E del T, n constant, is just 3n Kb. And this relation that you have is called the Dulong-Petit's law. This is the energy of the system as a function of temperature. Now, surprisingly, here, for an ideal gas, there is a difference. And for an ideal gas, we had 3 by 2 nkBT. On the other hand, here, I have 3 nkBT. And the reason behind that lies in the Hamiltonian. In the ideal gas, the Hamiltonian did not have this contribution, from the coordinates. It only had the contribution from the momenta. So this extra degree of freedom actually contributes additional 3 by 2 nkBT, so that the total energy goes to 3 nkBT. Right? So with this discussion, we are going to conclude our microcanonical ensemble. and then we are going to move on to canonical ensemble.